The research explores the application of reaction-diffusion equations, RDEs, to model spatiotemporal evolution in density fields, focusing on aggregation phenomena. A specific RDE with quadratic diffusivity is considered, exhibiting negative diffusivity for U element of A, B. Nonclassical symmetry techniques are employed to construct time-dependent, colliding wave, and receding traveling wave solutions. These solutions are initially multi-valued but become single-valued through shock insertion. The paper examines the properties of these solutions, including Stefan-like boundary conditions and phase plane analysis. It also investigates the spectral stability of the U equals 0 and U equals 1 constant solutions, providing proof for certain values of A and B that receding traveling waves are spectrally stable. The authors introduce a new concept related to these solutions, contributing to the understanding of RDEs with negative diffusivity and shedding light on the complex interplay between diffusion and local density field changes. This work has implications for fields where aggregation is preferred, such as biology, chemistry, and physics. The paper delves into the concept of nonclassical symmetry in reaction-diffusion equations, which are partial differential equations, PDEs, with applications in various fields such as wound healing, biological invasion, and movement through porous media. These models describe the evolution of one population in one spatial dimension and have the general form of a PDE that combines linear Fickian diffusion with a reaction term. However, many systems exhibit nonlinear diffusion, where the diffusivity d, U, is not constant but depends on the density U. This paper focuses on models with positive diffusivity, resulting in population dispersal from high to low density regions, and those that involve aggregation, where individuals move up density gradients from low to high density regions. The authors introduce a new shock condition for nonclassical symmetry, where the diffusivity and flux are continuous across the shock, recovering the equilaria rule for symmetric diffusivity and resulting in a different shock position for non-symmetric diffusivity. The study employs spectral stability analysis and phase plane analysis to understand the behavior of these models, shedding light on their implications for biological phenomena like aggregation. In reaction-diffusion equations, RDEs, for modeling aggregation, negative diffusivity can emerge from discrete models featuring social aggregation, enabling aggregation without chemotaxis. This phenomenon is observed in models where diffusivity is 0 at the boundaries and negative within a specific range. However, the introduction of negative diffusivity leads to ILL-posedness in initial value problems, resulting in solutions with steep gradients and potentially multi-valued solutions. To address this issue, the technique of inserting a shock is employed, which enables a single-valued solution by introducing an instantaneous jump in the density. This approach, well established for hyperbolic equations, has been successfully extended to diffusion equations with negative diffusivity. The shock insertion technique allows for the existence of shock-fronted traveling waves, a phenomenon of particular interest in reaction-diffusion models. In these models, the negative diffusivity induces a localized increase in density, which can lead to the formation of aggregates. The shock-fronted traveling waves, in turn, facilitate the propagation of these aggregates, enabling the study of their dynamics and interactions. The incorporation of negative diffusivity and shock insertion techniques provides a novel framework for modeling aggregation phenomena, offering insights into the complex behaviors of social aggregation systems. The application of nonclassical Lie symmetry is demonstrated in this section for the construction of a multivalued analytic solution to the reaction-diffusion equation, RDE, with negative diffusivity. This approach involves identifying invariant quantities within the equation and utilizing them to formulate solutions. The authors employ a specific nonclassical symmetry, independently discovered by Arrigo and Hill, and Gord and Broadbridge, to derive an analytic solution. By applying this symmetry, the RDE is transformed into a unidimensional spatial Helmholtz equation, which is then solved. The resulting solution is shown to satisfy the relationship between the reaction and diffusion terms, thereby ensuring the absence of singularities. This methodology enables the construction of solutions for arbitrary diffusivity, provided the reaction and diffusion terms meet a certain condition. The Kirchhoff transformation plays a crucial role in understanding the behavior of the density U, x, t. This transformation, denoted by phi, u, is intimately connected with the Helmholtz equation. By solving the Helmholtz equation and inverting the Kirchhoff transformation, we can obtain the solution for u, x, t. Focusing on the specific case where kappa equals k2 less than 0, we find that the solution for psi, x, takes the form of exponential functions. Inverting the Kirchhoff transformation using the exact form of psi, x, enables the construction of analytic solutions. Furthermore, we investigate a model with a quadratic function for d, u, which yields time-dependent and receding sharp-fronted traveling wave solutions. The analysis also explores shock-fronted solutions and the stability of both constant and traveling wave solutions. Notably, the relationship between two key rules is established. The phi, u, is continuous rule and the equal area in phi, u, rule. This lays the groundwork for the subsequent analysis, which delves deeper into the properties of the Kirchhoff transformation and its implications for the behavior of u, x, t. The authors explored three analytic solutions for the reaction-diffusion equation, RDE, with a quadratic diffusivity, d, u, equals, ua, ub, where a, b element of 0, 1, and a less than b. This form of diffusivity is motivated by previous works, including Johnston et al. And Turchin, who derived reaction-diffusion models with negative diffusivity from discrete models. Lee et al. Showed that traveling wave solutions exist for the RDE with quadratic diffusivity. The quadratic diffusivity is illustrated in Figure 1a, with a equals 0.2 and b equals 0.4. To utilize a nonclassical symmetry, the authors obtain the corresponding reaction term using equation 2, and fix one of the zeros of the reaction term to be at u equals 1, ensuring phi 1 equals 0 and r 1 equals 0. By choosing a equals kappa d 0, they enforce r 0 equals 0. The reaction term r u has a third zero at u equals a plus b. The authors identified two possible types of reaction terms for this quadratic diffusivity. When a plus b less than 1, the reaction term is typically negative for lower densities and positive for higher densities, allowing for the possibility of population growth or decline depending on the density. This scenario is explored further in the study. In contrast, when a plus b is greater than or equal to 1, the reaction term is typically negative for all values of u in the range of interest, leading to a decrease in population for all densities, and is not investigated further. The authors draw an analogy between the reaction term in their model and the cubic reaction term commonly used to model changes in gene frequencies or population dynamics due to the Allais effect. This reaction term, denoted by r, u, exhibits singularities at u equals a and u equals b, as indicated by the solid vertical lines in Figure 1b. Between these singularities, r, u, becomes large and positive. However, the shock solutions constructed in this work avoid the u values in this region. An example of a nonlinear diffusivity, reaction function, and flux potential is presented in Figure 1. Here, the diffusivity, denoted by kappa, is set to 1, while the parameters a, u, a, and b are set to 0.08, 1, 0.2, and 0.4, respectively. The vertical lines in Figure 1 indicate the locations of the zeros of the diffusivity, while the reaction term has zeros at u equals 0, u equals a plus b equals 0.6, and u equals 1. To construct an analytic solution to the nonlinear partial differential equation, 1. The authors employ the Helmholtz equation, 3. To solve for the function psi, x, and subsequently invert the Kirchhoff transformation, 4. To obtain u, x, t. Since the diffusivity is quadratic, the Kirchhoff variable phi, u, will be cubic in u, x, t, and the Kirchhoff transformation determines the solution implicitly. The solution to the partial differential equation describing the evolution of a scalar field is given by phi, u, equals 1/6, u1, 2u squared plus 23a3b, u plus 23a3b plus 6ab, where a and b are constants. This solution is multivalued in a region centered around the points where the diffusivity is 0, u equals a and u equals b. To recover a single-valued solution, a shock discontinuity must be inserted in this multi-valued region. The flux potential phi, u, is conserved across the shock, and the equation can be rewritten as partial differential u, partial differential t equals squared, partial differential x squared phi, u, plus r, u, where r, u, represents the source term. The solution is obtained using nonclassical symmetry solutions, and the boundary conditions will determine the values of the constants of integration C1 and C2. The diffusivity is negative in the region U element of A, B, leading to a multivalued solution in this range. The flux potential phi, U, is increasing except in the region U element of A, B, where it is decreasing. The solution is single-valued outside of this region. The authors impose continuity of the flux potential phi, U, equals d, u, across the shock, which determines the shock position based on two conditions. Phi, ul, equals phi, and phi, ul, equals d, ul, equals d, equals phi, These conditions are satisfied when the left and right endpoints of the shock, ul and are given by equation 10 for quadratic diffusivity, under the assumption b less than a. 2 plus square root 3, ensuring ul greater than 0. The reaction term r, u, is also conserved across the shock due to its relationship with the diffusivity, as shown in equation 2. Both ux and ut are conserved across the shock, demonstrating the conservation of phi, u, equals d, u, and r, u, across the discontinuity. Figure 2 illustrates the behavior of the diffusivity and reaction term across the shock. The dashed horizontal line in Figure 2a shows that the solution jumps over the zeros of the diffusivity and the region where d, u, less than 0, conserving phi, u, equals d, u. Figure 2b shows the solution jumping over the locations where the reaction term is singular and the region where it is positive. Figure 2c displays the flux potential around the shock, illustrating the conservation of phi, u, across the shock. The authors present examples of analytic time-dependent solutions by adjusting the constants C1 and C2 in equation 7. For instance, setting C1 less than 0 and C2 equals C1 yields a receding solution that satisfies U, 0, t, equals 1 for all t, with the shock persisting despite the solution becoming steeper as the front approaches x equals 0. This solution is shown in Figure 3a. Alternatively, by imposing C1 less than 0 and C2 less than 0, the authors obtain a different solution, also displayed in Figure 3. Around the shock, nonlinear diffusivity, reaction function, and flux potential are depicted in the figure. The parameters employed are kappa equals 1, a equals 0.08, u equals 1, a equals 0.2, and b equals 0.4. Providing a detailed view of the shock's behavior and underlying dynamics. The vertical lines indicate the zeros of the diffusivity. Notably, the reaction term is 0 at 3 distinct points. U equals 0, U equals A plus B equals 0.6, and U equals 1. This setup enables a nuanced understanding of the shock's behavior and the intricate dynamics that govern it. Time-dependent solutions of a reaction-diffusion equation are explored, focusing on nonclassical symmetry solutions characterized by sharp fronts. These fronts can be either receding or colliding waves, as depicted in Figure 3. In the receding wave solution, the density U, x, t, is non-negative for x element of 0, L, t, where L, t, is a moving boundary that evolves with time, describing the position of the sharp front. The colliding wave solution also exhibits a time-dependent behavior, becoming smooth at later times and eventually becoming 0 everywhere. The analysis utilizes the nonclassical symmetry approach, which does not require imposing conditions on the gradient ux at the moving boundary. Instead, the condition arises as a consequence of the non-negative u requirement. Solutions are generated using specific parameters, such as kappa equals 1, a equals 0.08, u equals 1, a equals 0.2, and b equals 0.4. The page highlights the importance of restricting the domain to ensure that the density remains non-negative, a crucial aspect in biological and chemical applications where u, x, t, represents a concentration. The results presented demonstrate the versatility of the nonclassical symmetry approach in generating novel solutions to reaction-diffusion equations, providing insights into the dynamics of various physical and biological systems. The authors of this research paper approach the solution to a partial differential equation, PDE, by framing it as a moving boundary problem, akin to the classical Stefan problem. In the Stefan problem, the linear heat equation is solved on a domain X element of 0, L, T, where the boundary L, T, evolves according to the Stefan condition, which relates the boundary speed to the flux at the boundary. However, the author's analytic solutions do not satisfy this regular Stefan condition, instead obeying an alternate condition where the boundary speed is inversely proportional to the gradient, as expressed in equation 12. This Stefan-like condition is satisfied by both the time-dependent and colliding wave solutions, as shown in Figure 3. The physical or biological interpretation of this condition remains to be determined, but similar moving boundary conditions have been reported in the literature. A key consequence of this condition is that the boundary speed L, T, is negative in both the traveling wave and time-dependent solutions, resulting in receding density profiles. This behavior is unusual in reaction-diffusion models but is reminiscent of recent adaptations of the Stefan problem to solve reaction-diffusion equations on moving boundaries. The authors highlight that the inverse relationship between the gradient and boundary speed, as expressed in equation 12, implies that steeper density gradients led to slower boundary speeds. This has implications for the dynamics of the system, particularly in the context of reaction-diffusion models. The author's novel approach to solving the PDE using a moving boundary problem framework provides new insights into the behavior of these systems and warrants further exploration. The analysis on page 13 examines the relationship between front speed and gradient depth, revealing that slower fronts are associated with larger flux at the boundary, whereas faster fronts have smaller flux. It discusses a receding traveling wave solution, where the implicit solution for phi, u, is derived in terms of the traveling wave coordinate z. This solution showcases a multi-valued nature around regions with negative diffusivity, illustrated in Figure 4 by the insertion of a shock to ensure constant diffusion. The discussion emphasizes the importance of requiring R0 equals 0 to avoid negative diffusivity regions and singularities. The analysis also satisfies the Stefan-like condition at the location where u equals 0, demonstrating the sharp front's coincidence with z equals 0. The paper delves into the realm of traveling wave solutions and their characteristics, particularly emphasizing the movement of boundaries and fluxes. A visual representation of this concept is presented in Figure 4, where blue curves signify the solution at different times, with red stars marking the initiation and termination of the vertical shock, and horizontal lines indicating where the diffusivity is 0. The dashed curve in Figure 4b illustrates the multi-valued part of the solution at a single time, given specific parameter values for kappa, a, u asterisk operator, a, b, c1, and c2. In Figure 5, the authors compare the traveling wave solution with time-dependent solutions, highlighting the inverse relationship between the speed of the moving boundary and the flux at the boundary for time-dependent solutions. For the colliding wave solution, the dash dot curves, green, in Figure 5 are multi-valued due to the presence of two contact lines, resulting in an increase in the speed of the moving boundaries and a decrease in the flux at both boundaries as they approach 0. The boundary position and flux for receding time-dependent, colliding wave, and traveling wave solutions are key areas of focus. The colliding wave solution stands out for its multi-valued dash dot curves, a characteristic inherent to its nature. The traveling wave solution, on the other hand, is notable for being compactly supported with a sharp front, and it can be sustained by a model with a positive reaction term in the range 0, UA. The analysis of the receding traveling wave solution involves a transformation to the z-coordinate, leading to an ordinary differential equation. This is further simplified into a system of equations, which is used to discuss the wall of singularities that arises when d, u, equals 0. The discussion centers on the impossibility of smooth solutions between u equals 0 and u equals 1 in System 18, due to singularities and the necessity of shocks. Singularities are points where solutions cease to exist, except at specific points known as holes in the walls. In the phase space, it is evident that shocks are required, and the solution cannot be represented by a single trajectory but rather a combination of two solution branches. This is demonstrated through Figure 6, which presents a phase-plane portrait of system 18. The analysis will proceed with a stability analysis of constant and traveling wave solutions to the original system. In the context of a mathematical model, Figure 6 illustrates the phase portrait of a system described by equation 18, with arrows indicating the direction field and a dashed curve representing the solution trajectory that emanates from 1, 0, and terminates at 0, q0, satisfying the boundary condition 12. The phase portrait features vertical lines denoting walls of singularities, a solid horizontal line, and a curve representing the nulk lines of the system. A perturbation analysis is conducted for epsilon much less than 1, yielding a partial differential equation, PDE, for the perturbation P, given as equation 19. This equation is derived by collecting terms of O, epsilon, as epsilon right pointing arrow 0. For special solutions considered in this work, the operator L, U, depends on either a constant coefficient or a single variable only. A linear stability analysis is performed for constant solutions, assuming that the solution U is either 0 or 1. In this case, equation 19 becomes a constant coefficient second-order PDE, which can be solved using separation of variables. Assuming that P, x, t, has the form P, x, t, equals e caret lambda Tp, x, we obtain the ordinary differential equation, 20. This equation is crucial for understanding the stability properties of the constant solutions within the context of the mathematical model. In reaction-diffusion systems, the stability of constant solutions is a crucial aspect of understanding pattern formation in dynamics. This research focuses on the stability of such solutions governed by a reaction-diffusion equation, where perturbations are chosen in the L2, R, domain to ensure boundary conditions and facilitate the application of the Fourier transform. The derived dispersion relation, lambda, reveals that perturbations decay to the constant solution if the real part of lambda is negative. For the special case of U equals 0, the stability of the constant solution depends on the sign of R, 0, which is influenced by the positive parameters A and B. Consequently, the constant solution U equals 0 is stable. The stability of U equals 1 is also analyzed, with the sign of R, 1, depending on the ratio of D, 0, to D, 1. The investigation highlights the critical role of quadratic diffusivity and reaction terms in determining the stability of solutions. These findings provide valuable insights into the complex interplay between diffusivity, reaction kinetics, and pattern formation in reaction-diffusion systems. The quadratic diffusivity and reaction terms are shown to significantly impact the stability of constant solutions, emphasizing the need for a nuanced understanding of these terms in modeling reaction-diffusion systems. The study's results have important implications for understanding the dynamics of pattern formation and stability in various contexts, from biological systems to chemical reactions. The stability analysis of a quadratic diffusivity model is discussed in the paper, focusing on the reaction-diffusion equation where the reaction term is quadratic in U and the diffusivity is linear. For constant solutions, the solution U equals 1 is stable when A plus B less than 1 and unstable when A plus B greater than 1, with long wavelength instabilities occurring for sufficiently small alpha in the latter case. The authors then perform a linear stability analysis for receding traveling wave solutions, considering perturbations of the form P, Z, E caret, lambda T. The linearized equation, given by 25, depends only on Z and requires P, Z, to be square integrable on infinity 0, vanish at Z equals 0, and be C1 across the shock. The spectral stability of the receding traveling wave solution is discussed using the notation from Capitula and Promislo, 21, where the spectrum of L, U, consists of all lambda element of C such that L, U, lambda does not have a bounded inverse on L2_0, infinity, 0. The concept of spectral stability is introduced, where a wave solution is considered spectrally stable if any eigenvalue lambda of the linearized operator L, U, has a negative real part, denoted as Re, lambda, less than 0. Theorem 2.1 states that the traveling wave solution found in section 2.3 is spectrally stable, provided certain conditions on the parameters A and B are satisfied. Specifically, 1/2 d, U, ZZ plus R, U, less than 0 for U element of 0, ul, union, 1, implies R, 1, less than 0. The proof of Theorem 2.1 begins with an analysis of the far-field operator of equation 25. As Z approaches negative infinity, solutions to equation 25 behave like solutions to the constant coefficient ordinary differential equation 26, which has a characteristic equation 27 with characteristic exponents given as the roots r plus or minus. The sign of the real parts of r plus or minus is of interest, and by assuming r equals I alpha for alpha element of R, the dispersion relation 28 is obtained, which is a parametrized curve for lambda in the complex plane, parametrized by alpha. The authors analyze the dispersion relation in the complex plane, dividing it into two regions, omega and b. In omega, Re, r plus, is greater than 0, and Re, r, is less than 0. In b, both Re, r plus, and Re, r, are greater than 0, indicating that L, U, lambda is not invertible. Solutions in omega decay to 0 as Z approaches negative infinity, and the solution satisfying the right-hand boundary condition lies in the kernel of L, U, lambda. This implies the spectrum contains the closure of B due to its closure. The authors also show D, 1, is greater than 0, and the maximum real value of lambda depends on R, 1, which is negative under specific conditions. This has significant implications for the invertibility of L, U, lambda and the behavior of solutions in different regions. The calculation on page 22 of the research paper continues to explore the invertibility of the operator L, U, lambda, focusing on the computation of the Fredholm index and its implications for eigenvalues. It is shown that any eigenvalues must be real, and for certain conditions, they must be negative. This is achieved by multiplying equation 25 by an integrating factor to put it into Sturm-Liouville form, allowing for the analysis of the eigenvalues of the system. The functions S1, S2, and S3 are defined in terms of D, U, which are essential in determining the properties of the eigenvalues. The paper also highlights the importance of the positivity and boundedness of S3, a key function in the analysis. This section provides a crucial step in understanding the stability of the shock solutions and their properties under various conditions. The weighted Hilbert space properties are discussed, focusing on the eigenvalues of the operator L, U, in L2, 0, minus infinity, 0, S3. It is established that for lambda element of omega, the eigenvalues are real and negative. The discussion involves the weighted norm, the decay of solutions, and the self-adjointness of the operator. Equations 32, 33, and 34 are derived through mathematical manipulations, showcasing the diffusion and speed terms. These equations are crucial for understanding the behavior of eigenfunctions and eigenvalues in this space. The authors present the final step in proving Theorem 2.1, establishing the spectral stability of receding traveling waves with quadratic diffusivity. They introduce the expression for the eigenvalue lambda, given by equation 35, which involves integrals related to the diffusivity d, u, and the reaction term r, u. The first integral represents the contribution from the region to the left of the shock, while the second integral represents the contribution from the region to the right of the shock. The authors specify the form of the diffusivity d, u, and its derivative d, u, which is positive when u greater than a plus b, 2 and negative when u less than a plus b, 2. They also show that certain terms are negative and that others will vanish if specific conditions are met. The authors argue that the entire term S will be negative, implying that any real eigenvalues of L, U, in omega will be negative, thereby completing the proof of Theorem 2.1. The stability analysis is numerically explored, and the results are presented in Figure 8, showing that A, B, pairs that satisfy the stability condition D, U, ZZ, 2 plus R, u less than 0, as well as b less than a 2 plus square root 3. The figure illustrates the values of a and b for which a plus b less than 1 and 0 less than b less than 1. It shows circles, blue, representing pairs that satisfy the conditions for spectral stability outlined in Theorem 2.1, as well as the condition b less than a 2 plus square root 3, ensuring ul greater than 0. Conversely, crosses, red, denote combinations of a and b that do not meet both conditions. The analysis confirms spectral stability for a, b pairs marked by blue circles, but does not make any statements about the stability of a, b pairs indicated by red crosses. The left border of the circle, blue, region is determined by the condition b less than a 2 plus square root 3, while the top right border is determined by the stability condition d u zz 2 plus r u less than 0. This section also discusses the equal area rule and non-symmetric diffusivity, where shock solutions are constructed by connecting two branches of an analytic multivalued solution. The shock location is chosen according to the conditions described in equation 9, and as shown in figure 9. In the context of shock location in multivalued regions, two conditions are required to determine the shock position. The first condition, expressed in equation 9, ensures the continuity of the diffusive flux across the shock, a constraint widely used in previous works, such as 2640. The second condition, corresponding to the equal area in phi u rule, is given by equation 37, which is illustrated in figure 9b. This rule has been employed in various studies, including Pego's work on nonlinear Cahn-Hilliard equations, 32, Witelski's research on diffusion equations with non-local regularization, 40, and Lee et al.'s investigation of reaction-diffusion equations, 26. The equal area rule arises from the use of non-local regularization, as seen in equation 38, where epsilon is a small parameter. This type of regularization has been utilized in conjunction with reaction terms to construct shock solutions, 26. Other regularization methods, including composite regularizations, have also been employed to obtain shock solutions, 26, 5. Recalling section 2, the shock location is determined by the requirement that the derivative of the flux potential phi u must be continuous, satisfying conditions 9 across the shock. As a result, the diffusivity remains constant across the shock, and in the case of the symmetry solution presented, the reaction term is also constant. The condition on the first derivative recovers the equal area rule, 37, for quadratic diffusivity. This paper demonstrates that this holds true for any diffusivity with two zeros and symmetry about the midpoint of its zeros. In the context of shock solutions for scalar conservation laws, we examine the properties of diffusivity functions with two zeros, d a equals d b equals 0, and d u less than 0 for a less than u less than b. By introducing the variable u equals u, a plus b, 2, the diffusivity function d, u, becomes an even function with two zeros at plus or minus a, where a equals ab, 2. The transformed flux function phi, u, is a vertical translation of an odd function, f, u, equals phi, u, u equals 0. We analyze the equal area rule for phi, u, which requires that the areas in the two lobes cut off by the horizontal line phi ul equals phi or equal. Since phi, u, is a vertical translation of the odd function f, u, the requirement that phi ul equals phi is satisfied by ul equals This implies that phi ul equals phi ul, and thus phi ul equals phi u equals 0. The left-hand side of the equal area condition is then transformed into an integral of the odd function f u over the interval ul By introducing the even function f u equals integral f u du, the equal area condition simplifies to f ul equals f ul equals 0. This result demonstrates that the equal area rule is automatically satisfied for diffusivity functions with two zeros, provided they are symmetric about their midpoint. This finding has implications for the study of shock solutions in scalar conservation laws and could potentially lead to new insights into the behavior of these systems. In the context of nonclassical symmetry, the equal area rule for shock location in a reaction-diffusion equation is equivalent to the requirement that phi, u, be continuous, provided the diffusivity is symmetric about the midpoint of its two zeros. However, if the diffusivity is not symmetric, this equivalence does not hold, and the equal area rule and the continuity of phi, u, yield different shock locations. The paper illustrates this discrepancy using a quadratic diffusivity function with two zeros at u equals a and u equals b, where a less than b, a, b element of 0, 1, and c is an arbitrary constant. The diffusivity is not symmetric about the midpoint of its two zeros. A corresponding reaction term is chosen to mimic the characteristics discussed in section 2. The paper shows that when phi, u, is continuous, both the diffusivity and reaction term are continuous across the shock, whereas enforcing the equal area rule results in a different shock location and discontinuity in both the diffusivity and reaction term. An implicit solution to the reaction-diffusion equation with the given quadratic diffusivity and reaction term can be constructed using the nonclassical symmetry described in section 1. The paper presents a receding traveling wave solution, highlighting the difference in shock location as chosen by the requirement that phi, u, is continuous and the equal area rule. This discrepancy underscores the importance of considering the symmetry properties of the diffusivity when applying these methods for locating shocks in reaction-diffusion equations. The figure illustrates the analytic solution to the reaction-diffusion equation with non-symmetric diffusivity. The parameter values are kappa equals 1, a equals 0.0448, a equals 0.2, b equals 0.4, c equals 0.6, and d equals 0.2. The diffusivity d, u, is shown, with an inset depicting the transition across the shock. The reaction term r, u, is given by equation 2. The figure also includes a multi-valued traveling wave solution, where curves show the solution at different times, and horizontal lines indicate where the diffusivity is 0. An enlargement of the multi-valued part of the solution is provided, highlighting the endpoints of possible shock positions. The applications of nonlinear reaction-diffusion equations in physical sciences are extensively discussed, with a focus on non-classical symmetry analysis. This analysis enables the recovery of analytic solutions for specific diffusivity and reaction terms, including scenarios with negative diffusivity. Negative diffusivity is described as providing a phenomenological description of aggregation, which is also observed in the continuum limit of discrete models with aggregation. The presence of shock discontinuities in the analysis of analytic solutions to reaction-diffusion equations with nonlinear diffusivity is highlighted. The section emphasizes the importance of constructing and analyzing exact symmetry solutions rather than imposing arbitrary initial conditions using non-classical symmetry techniques. It also notes the connection between nonlinear reaction-diffusion equations with negative diffusivity and aggregation phenomena in physical or biological systems as an area for further investigation. The research focuses on resolving regions of multi-valued solutions in reaction-diffusion equations by placing shocks to ensure continuity of the flux potential and its derivative. This approach is particularly relevant for symmetric diffusivity, recovering the shock with the longest possible length. The study also analyzes the stability of constant and traveling wave solutions, showing that the constant solution u equals 0 is stable, while u equals 1 exhibits long wavelength instability for certain diffusivity values. Additionally, the analysis of traveling wave solutions with quadratic diffusivity is proven to be spectrally stable for specific parameter combinations. The research emphasizes the importance of understanding the link between negative diffusivity and physical phenomena, highlighting the need for further investigation into entropy jumps and regularization techniques. In the realm of nonlinear reaction-diffusion equations, defining shocks is a complex endeavor that necessitates specific conditions. A key requirement for this process is the continuity of the function phi, u, which in turn demands a particular regularization of the equation. This regularization plays a pivotal role in understanding shocks and should be thoroughly investigated as part of future research. Additionally, examining the jump in entropy across the shock is crucial for a comprehensive understanding of these phenomena. The authors acknowledge the support they received from the Australian Research Council and other organizations during their research. The authors provide a comprehensive literature review on reaction diffusion models, highlighting the significance of exact solutions, nonclassical symmetries, and inverse density dependence in understanding biological spread and population dynamics. They cite the work of Broadbridge et al. 6. On exact solutions to the Huxley and Fisher equations for gene propagation and Broadbridge et al. 7. On conditionally integrable PDEs and nonclassical symmetries. The concept of inverse density dependence and the Allais effect, as explored by Korchamp et al. 8, is also discussed. The review further includes the spreading-vanishing dichotomy in the diffusive logistic model with a free boundary, studied by Du and Lin, 9, and compactly supported solutions of reaction diffusion models of biological spread by Edwards et al. 10. The authors also reference the work of L. Hatcham et al. 11, on the Fisher-Kolmogorov-Petrovsky-Piskunov equation and L. Hatcham et al. 12, on invading and receding sharp-fronted traveling waves. The literature review concludes with references to Faday's 13 work on semi-infinite traveling waves and Ferracuti et al. 14 on traveling waves in reaction diffusion equations. The authors on page 34 of the research paper outline a comprehensive list of key findings and methodologies, including a detailed explanation of the novel algorithm they've developed. This algorithm, designed to optimize data processing, significantly enhances the efficiency of complex computations. The authors also discuss the mathematical underpinnings of their approach, emphasizing the importance of precision in data manipulation. In the realm of complex systems, mathematical models and techniques are essential tools for understanding behavior and dynamics. This section of the research paper delves into diffusion aggregation processes, focusing on monostable reaction terms. It draws from Kuzmin and Ruggerini's work on front propagation in diffusion aggregation models with bistable reactions, providing valuable insights into the spread of invading organisms. The paper then explores various mathematical models and techniques that can be applied to these systems. One such technique is the use of partial differential equations, PDEs, which describe how a quantity changes with respect to space and time. These equations are crucial in modeling complex systems as they capture the spatial and temporal evolution of variables such as population density or chemical concentrations. Another key aspect discussed is the concept of pattern formation, where spatially inhomogeneous distributions emerge from initially uniform conditions. This phenomenon is often observed in biological systems, such as the formation of stripes or spots on animal coats, and can be modeled using reaction diffusion equations. These equations consist of a diffusion term representing the spread of a substance, and a reaction term describing the interactions between different components of the system. The paper also touches upon the idea of Turing instability, a mathematical concept proposed by Alan Turing that explains how patterns can arise spontaneously in systems due to differences in diffusion rates between components. This theory has been widely applied in various fields, including biology, chemistry, and physics, to explain observed patterns and behaviors in complex systems. Moreover, the paper discusses the role of nonlinearity in these systems, which refers to the relationship between cause and effect not being directly proportional. Nonlinear effects can lead to rich and diverse behaviors, including oscillations, chaos, and even self-organization. Understanding these nonlinear interactions is crucial for accurately modeling and predicting the behavior of complex systems. Finally, the paper highlights the importance of numerical simulations in studying these systems. Due to the complexity of the underlying mathematics, analytical solutions are often impossible to obtain, making numerical methods essential for gaining insights into the dynamics of complex systems. These simulations allow researchers to explore different scenarios, test hypotheses, and validate theoretical predictions against experimental data. In conclusion, this section of the research paper provides a comprehensive overview of the mathematical models and techniques used to understand the behavior of complex systems, particularly those involving diffusion aggregation processes with monostable reaction terms. By employing PDEs, reaction diffusion equations, Turing instability, nonlinearity, and numerical simulations, Researchers can gain valuable insights into the intricate dynamics of these systems, shedding light on their underlying mechanisms and potential applications in various fields. In the realm of mathematical modeling, various equations and algorithms have been developed to describe and predict complex phenomena in biology, ecology, and physics. The Lotka-Volterra equations with chemotaxis, for instance, capture the intricate interactions between species and chemical signals. These models provide insight into the dynamics of predator-prey relationships and how they are influenced by environmental cues. Another significant application of mathematical modeling is in the study of liquid monolayers. The spreading of these molecular layers can be modeled using equations that account for intermolecular forces, surface tension, and other physical properties. This understanding is crucial for fields such as materials science and biophysics, where the behavior of molecules at interfaces plays a critical role. Mathematical models also play a key role in understanding biological processes, particularly in wound healing. Models of epidermal wound healing simulate the migration and proliferation of cells during the repair process, shedding light on the factors that influence wound closure rates and tissue regeneration. This knowledge has important implications for the development of new treatments and therapies. Ecological conservation is another area where mathematical modeling is essential. The Allais effect, which describes the relationship between population size and individual fitness, highlights the importance of maintaining minimum viable populations to ensure species survival. Models incorporating this concept help conservationists devise strategies to protect endangered species and preserve biodiversity. These examples illustrate the breadth and depth of mathematical modeling in various scientific disciplines. By providing a framework for understanding complex systems, these models enable researchers to make predictions, test hypotheses, and inform decision-making processes. As our understanding of these models continues to evolve, so too will our ability to address pressing challenges in biology, ecology, and beyond.